I am Antonio, and today with Francesco, we are going to present GDPR and beyond, demystifying data governance challenges. Francesco and I are data architects at Agile Lab, an Italian consulting firm specializing in large-scale data management. Agile Lab is an effective and dynamic company structured around an holacracy-inspired model with multiple business units. Through these business units, we are lucky enough to have several Fortune 500 companies as our customers. Okay, let's take a look at what we have in the agenda today. We will talk about data privacy and GDPR, why this European regulation is so important and we should design systems to be compliant with it. We will have an overview of different techniques that we can leverage to be compliant and secure, like anonymization and encryption. Then we will compare these different techniques, focusing our attention on pros and cons of each one. Finally, we will present a viable data sharing strategy for a real use case. Data is the new oil, am I right? Data is the fuel for innovation. Machine learning, artificial intelligence, and analytics simply can't be possible without it. Just as oil power engines, data fuels algorithms, enabling machines to learn and improve over time. This is the case for machine learning. Also, data is the lifeblood of AI, driving smart ecosystems that can mimic human intelligence. Finally, data analytics extracts valuable insights just as refining oil produces useful products. Yeah, data is the new oil. Is the new oil also in the bad parts of it? For example, data breaches are very similar to oil spills. They cause extensive damage and leak sensitive information that erode trust of our customers. We can also have privacy violations, which are very similar to the pollution that can harm ecosystems. Privacy violations disrupt the digital environment and harms individuals. Then we have regulatory fines, which are very comparable to environmental fines, which means that when your data is non-compliance with data protection regulation, you will get very huge fines. Finally, you will suffer for reputational damage because, like environmental damage, data breaches can severely impact brand trust and loyalty. So let's reflect on the reality of data breaches over the past 20 years. This visualization showcases the top 50 biggest data breaches from 2004 to 2021. 17 billion records were compromised. As we can see, the severity of breaches has escalating during the years, particularly from 2016 onwards, with the web sector being the hardest hit, accounting for nearly 10 billion records lost. Significant breaches span across various sectors, including finance, government, and tech, highlighting the widespread vulnerability. Notable breaches include Yahoo 2013, losing 3 billion records, and Facebook in 2019, with 530 million records exposed. This growing trend underscores the critical need for robust data security measures. These breaches not only compromise personal information, but also erode public trust and pose severe financial risks. As we move forward, it's imperative to prioritize data protection and adopt stringent security protocols to safeguard the digital assets. That's why European Union came up with GDPR. GDPR stands for General Data Protection Regulation and is a regulation that requires businesses around the world to protect the personal data and privacies of European Union citizens. Starting from on the 25th of May 2018, GDPR puts in place certain restrictions on the collection, use, and retention of personal data. Personal data is defined as information relating to an unidentified or identifiable natural person. This includes data such as name, email, phone number, in addition to data that may be less obvious like IP addresses, GPS location, phone ID, and more. GDPR is based on some key principles, and we will briefly run. First of all is lawfulness. Personal data must be processed legally, adhering to established laws, such as GDPR. Then we have fairness. Data processing should be fair, protecting vital interest, performing tasks carried out in the public interest, or pursuing legitimate interest of the data controller or a third party. Then we have transparency, because organizations must be open about their data processing activities. They should provide clear, accessible, and understandable information to individuals about how their data is being used, who is collecting it, and why. And this is why you have the cookie in every European website now. Then we have purpose limitation. So personal data must be collected for specified, explicit, and legitimate purposes, and not further processed in a manner that is not compatible with those purposes. Then you have the data minimization principle. That means organizations should collect only the personal data that is necessary to achieve the specified purpose. And we will have more on this later. Then we have accuracy. So personal data must be accurate and kept up to date. And inaccurate data should be corrected or deleted. Storage limitation means that personal data should not be kept longer than necessary for the purpose for which it was collected. For example, an example of storage limitation is the right to be forgotten. If I ask to be forgotten by some company, they should delete all data about me. This is storage limitation. Then we have integrity and confidentiality. So organization must ensure that the security of personal data, protecting it against unauthorized or unlawful processing, accidental loss, destruction, or damage, like data breaches. And then you have accountability. So data controllers are responsible for complying with GDPR principles and must be able to demonstrate their compliance. In order to do that, GDPR creates some requirements around the regulation itself. It requires that companies have data protection impact assessments, which are tools used to identify and mitigate risk associated with data processing activity. They must follow data breach notification regulations, so they should timely report data breaches to both authorities and individuals. Then they need to appoint a data protection officer, someone inside the company that ensure that there is a person responsible for overseeing data protection strategy and compliance with GDPR. Obviously, they need to implement data protection by design and by default. So every data initiative and the company should comply with this regulation without any need to integrate it after. And then they have some record keeping obligations. So they need to be sure that companies maintain a detailed record of their data processing activities, this for accountability and compliance purposes. Obviously, GDPR had huge implication for data governance. But what is data governance? Data governance is the process of managing the availability, usability, integrity, and security of the data in enterprise systems based on internal standards and policy that also control data usage. An effective data governance ensures that data is consistent and trustworthy and doesn't get misused. GDPR had some implication on internal data governance strategies for companies or enterprises, such as they had to enhance data security and privacy control to be compliant. They needed to improve data quality and accuracy because of the principle we've seen before. They need to put an increase to accountability and transparency in how data was used. And obviously, GDPR put pressure and created the necessity for regular audits and assessments around data. Today, we will focus mostly on the data minimization principle, which, in our opinion, is one of the most important ones in GDPR. Data minimization principle is foundational to responsible data handling and privacy protection. Under GDPR, data minimization principle mandates that organizations should only collect and process the personal data that is absolutely necessary for their specified purposes. Imagine you're building a house. You wouldn't order extra bricks that you'll never use, as it would be wasteful and clutter your space. Similarly, in data processing, we should avoid collecting excess data. By adhering to this principle, we not only streamline our data management practices, but also enhance security and compliance. Collecting minimal data reduces the risk of breaches and misuse, ensuring we respect our customers' privacy and build their trust. This also simplifies data management and can lead to more efficient processes. So let's commit to collecting only what we need, protecting privacy, and fostering a culture of data responsibility. So, does this meme look familiar? We know that people working on AI, machine learning, and analytics need real data to do their job. But this clashes with GDPR regulation 99% of the time. I will leave now the stage to Francesco, who will show you how we can build a compliant data sharing strategy and still allow data practitioners to be effective. Here you go, Francesco.
This meme will look familiar. This is a quite common scenario since most of ML engineers and data scientists need to prototype every day their models. In the majority of the cases, they start using development data, but the risk is that when moving to production, the performance of the model is low, so they fall back in using sampled data from production. This also increases the risk of sensitive data leakage and exposure in the minor environment. In the next slide, let's see how we can afford this issue and which techniques could help our case. So the first thing we are going to talk about is about anonymization. So that anonymization is one of the techniques that organization can use in order to adapt to strict data privacy regulation that require the security of personal identifiable information PII, such as health reports, contact information, and financial details. It differs from zero anonymization since it is not a reversible operation. Pseudo-anonymization simply reduces the correlation of data set with the original identity of a data subject and is therefore a useful but not an absolute security measure. And let's take a look now at the most common one technique about below the act of anonymization. The first one that we are going to talk about is generalization. Generalization usually changes the scale of the dataset, attributes, or the order of magnitude. As you may see, we have a simple table with several columns like name, age, birth date, state, and disease. In the example one, a field that includes number like age can be generalized by expressing an interval. As you may see, mark age has been put within an interval between 20 and 30. In the example 2, a field that includes dates like 1993, 1019 can be generalized by using only the year 1993. And this is the very first method. The other one is randomization. Randomization involves changing attributes in a dataset so that they are less precise while maintaining the overall distribution. Below the act of randomization, we have techniques such as noise addition and shuffling. Noise addition methods provide to inject some modification within the dataset in order to make it less accurate. For example, increasing or decreasing the age of a person, as we can see in our example inside the slide, while shuffling simply swap the age of Mark and John. And this is the second method. The third method is the most common one, is the suppression. Another useful technique, the most used in the space of anonymization, in my opinion. Suppression is the process of removing an attribute's value entirely from a dataset, while reduction removes part of the attribute value from a dataset. With such techniques, you can have multiple issues. For example, the warning number one is if the data is collecting for the purpose of determining at which age individuals are most likely to develop a specific illness condition, Suppressing the edge data would make the data itself useless. The warning number two is that the data type will change from integer to string, and this will break the contract for all the data consumer of that kind of data asset. In this slide, as you can see, we have a brief comparison of the methods explained previously. For each strategy, we evaluated three main factors: secrecy, privacy, and utility. And for each compost strategy factor, we assigned a rating ranging from poor to best. As you may see, every method has its weakness. So we do not have an evidence of a superior technique that could address all the items and factors around data. In this case, secrecy, privacy, and utility. What we can say is it depends a lot from the use case. But now let's take a look at the encryption methods in order to understand if they could help in the context of compliance. The first method we are going to talk about is format preserving encryption. Format preserving encryption, or FPE, is a symmetric encryption algorithm which preserves the format and of the information while it is being encrypted. FPE is weaker than advanced encryption standard, AES, but format preserving encryption can preserve the length of data as well as its format. FPE is by NIST standard, and there are three different modes of operation: FF1, FF2, and FF3. FPE works very well with existing applications as well as new applications. If an application needs data of a certain length and format, then FPE is the way to go. In order to operate with this cryptographic algorithm, you should use a secret key and a tweak. Another implementation is provided by Bouncy Castle, and the other one is available on Google Cloud as a loss prevention toolkit. Now that we have seen the first encryption method, let's take a look at another one: homomorphic encryption. Homomorphic encryption provides the ability to compute on data while the data is encrypted. It sounds like magic, don't you? There are three different modes in this case: partially homomorphic encryption that allows certain mathematical function to be used, for example, addition or multiplication. Somewhat homomorphic encryption. Some function can be performed only a fixed number of times or up to a certain level of complexity. Or, in the end, we have also fully homomorphic encryption that allows all the mathematical function, to be performed on unlimited times up to any level of complexity without requiring the decryption of the data. So suppose you want to operate on some sensitive data in the cloud. In the picture, you can have on the left the traditional approach. In the example, you can encrypt the files before moving to the cloud, for example, with a standard algorithm like AES. Then, if you want to perform some transformation on these files, you have to decrypt, apply the transformation, and then encrypt again. This will expose data at risk and also introduce a complex overhead. On the right side, instead, you are going to use the homomorphic encryption. Once you're on the cloud, you can do computation on ciphertext. Once you decrypt, you will obtain the same result of applying the function to the plain text data. Unfortunately, it requires a significant computational overhead to perform the intensive calculation, making this kind of strategy very slow and very resource intensive. In addition to performance concern, implementation of this specific algorithm can be very challenging and with highly complex techniques. Is it all? No, we have also other strategies and methods to present on the table. One of these is tokenization. Tokenization involves substituting sensitive data like credit card number with non-sensitive token, which are stored securely in a separate database called token book. Synthetic data is artificial data generated with the purpose of preserving privacy, testing system, or creating training data for machine learning algorithms. Synthetic data generation is a critical and very complicated for two main reasons: quality and secrecy. Synthetic data that can be reverse engineered to identify real data will not be useful in privacy context. Faker is a Python package that generates fake data for you. There is also Mokero that is another representative into the ecosystem of mock data that allows you to quickly and easily download large amounts of randomly generated test data based on the specification that you define. This is all in this case. Now let's have a look and summarize what we have learned in the previous slide. The first thing that you could do in order to have and to share data for machine learning purpose and analysis in minor environment is to use sample data coming from the production environment. The first thing, as a pro, you have realism. Sampled production data provide a realistic representation of actual data, helping developers and testers to identify issues that may not be evident with synthetic or mock data. You have an improved testing, so using real data allows for more comprehensive and accurate testing of functionalities, that integrity, performance, and scalability. Then you have stakeholder confidence. Using real data increase stakeholder confidence in the testing process and the reliability of the development lifecycle. Within the cons, you have a lot of issue with privacy and compliance. Even sample data can contain sensitive information, raising privacy concern and potential non-compliance with data protection regulations such as GDPR and other ones like HAPAA. Security risk. Using production data in minor environment like development or QA increase the risk of data breach and unauthorized access. Data freshness. This is another issue. Sample data might become outdated quickly, leading to scenarios where that environments are not completely aligned with current production environment. Let's take a look instead at synthetic data. Privacy and security is for sure are pros. So synthetic data can be generated without any real-world personal data, significantly reducing privacy concern and the risk of data leakage. Availability. Synthetic data can be created on demand. Efficiency. Generating synthetic data can be more cost-effective than collecting and labeling a large volumes of real-world data. On the contrary, what we have lack of realism. Synthetic data may not capture all the complexities and the nuance of the real-world data. We can have problem with overfitting. Also, there will be validation challenges. Validating the accuracy and the reliability of synthetic data can be very challenging, as it requires ensuring that the synthetic data closely mimics real-world data distribution. There is also concern about the complexity. It will require high setup complexity. Creating high-quality synthetic data will require sophisticated techniques and domain knowledge, making the initial setup complex and resource intensive. Encrypted data. So let's talk about it, focusing our attention on standard algorithm. Privacy protection. Anonymized data with encryption reduce the risk of exposing personal information. We are compliant in regulatory sense. Using anonymized data helps organizations to comply with GDPR, CCPA, and so on. We can enable easily a data sharing mechanism, and we can share this data with a little bit of freedom within department, organization, or also with external partners. We also have a risk mitigation because we are going to reduce the potential for data breach and misuse, as the data no longer contains personal identifiable information. But on the contrary, we have some complexity. Working with encrypted data, especially in the case of AES algorithm, can complicate development phase and also testing activities because data will lose any kind of meaning, will only keep its distribution. Key management challenges. Effective key management is crucial and can be complex, especially in non-production environment where multiple teams and individuals might need the access to encryption key. Limited testing accuracy. Testing with encrypted data may not reflect true application behavior if the encryption process introduces delays or errors that wouldn't be or wouldn't occur in production. Anonymized data. As we have seen before, it could be complex the anonymization process. Properly anonymizing data can be very challenging, requiring sophisticated techniques and ongoing management to ensure data remains anonymous. There is also the problem of re-identification on the data subject. There is a risk that anonymized data can be reverted, especially if combined with other datasets, for example, k-anonymity attack and so forth. In some cases, we lose the utility as we have seen for suppression. But now that we have summarized all the possible methods and techniques, at least the most important within the compliance context, let's take a look at the next slide. We are going to present a possible strategy for sharing data in a quite secure way in a binary environment. The practice I'm going to show you will combine some of the methods that we have seen before in the context of a data lake. So, before moving forward, let's have a little bit of context. We are in the cloud and we have a data lake. In the specific case, we leveraged the medallion architecture for our storage layer. The most of you already know what it is, a medallion architecture. It is also known as a multi-hop architecture. Data at each stage get enriched by increasing the intrinsic value. At each stage, PII can be present, and usually machine learning engineers and data scientists operate at silver gold layer. In this slide, let's see what we can do to share data in minor environments and enable a safe data consumption. This is a recipe for a cloud-based scenario, for example, AWS, but can be easily replicated in other cloud vendors. So you have a production account on the top, and for simplification purpose, an on-production account in the bottom. In each layer, we have the usual medallion architecture that we have seen before. The step one requires that data teams are in charge to productize their job and anonymize data. The encryption process becomes a mandatory step in the data lifecycle made of data ingestion, data normalization, and delivery. In step two, we will open a read-only cross-policy account from production to non-prod. The minor environment never writes to prod. It is only enabled for reading operation. The encryption key is never shared with minor environments. By this way, user personas that work in the lower environment are enabled in doing their job. Data engineer can prototype new silver dataset reading from the bronze encrypted layer. Analysts can model new schema and generate new anonymized report. Data scientists can prototype their model on quite realistic dataset since only sensitive column will be encrypted. Let's take a look at which are the benefits of this kind of practice and strategies. Analysts say format preserving encryption guarantees reference integrity, no schema change across different datasets, and allows to reuse business logic. Data jobs still works after the encryption. Data engineers are allowed to read only the encrypted layers leveraged an ad hoc IAM policy. This is going to simplify the data movement and the orchestration process between environments. Machine learning engineer can prototype and train their job models on a quite real data on a safe layer. DevOps practice is still in place since deployments of new artifacts and models can follow the standard CI/CD flow. SecOps says minimization principle is respected on minor end, since the most of the time you have encrypted information. Now let's take a look at the unknown feature, and let's talk about of the right to be forgotten below there ecosystem of GDPR. In this slide, we are going to talk and present the crypto shredding technique. Crypto shredding is the practice of deleting data by deleting or overriding the encryption keys. This is going to require that the data have been encrypted upfront. Deleting the key will automatically logically delete the record and all the existing copy, since all the encrypted info are not reversible anymore. This approach is very useful when you have multiple copies of data, for example, backup or multiple layers of data, like in the Mendelian architecture. If you are in the early stage of creating your data lake and building the foundation, you can combine crypto shredding and format preserving encryption in order to enable a very interesting scenario that will catch the secure data sharing practice that we have explained before and the deletion problem of multiple layers on environments. It is worthless to say that all these techniques and strategies will function with a strong data governance practice in place. Knowing in advance that where PII are stored and their lineage is fundamental. But this is another story. Thank you, everybody, and let's get in touch for any question and answer.